Welcome back, everybody. So today, instead of jumping on the computer, we are going to go over some examples of parameterized polynomial systems you will see all the time, okay? So in the last lecture, we talked about the parameter continuation theorem, which really the takeaway from that is that as long as you are using random parameters, you can relax and know that there's some well-defined number of isolated regular solutions. Okay, so that's the story. Which means that there's some proper subvariety called the exceptional set, which contains all the parameter values which give you strange behavior. You don't get the correct number of regular isolated solutions. And there are different reasons you could belong to that variety, and we discussed some of them, and some of them, you know, we discussed the subtleties of, for example, this delta infinity. But really, the thing you need to just remember is that such a delta exists, and as long as you're avoiding it, you're good to go. Okay, and for the most part, we are gonna avoid it. Okay. Okay, cool. So the first thing I want to do is place everything we've done so far into the context of this parameter homotopy story. Okay, starting with univariate polynomials. I want to solve some degree D polynomial. Okay. And what I want to do is I want to realize this polynomial system as one member of a family of a parametrized polynomial system. Okay. Does that make sense? I've already written it on the board. It's this. It's a square polynomial system because there's one equation, there's one variable, it has d plus 1 parameters. And what makes us happy is that we know a parameter which is easy to solve. And then we construct the straight line homotopy one minus t, sorry, one minus, sorry, 1 minus t times f of x with some c's plus gamma t times f of x at rp. It's called p. So our univariate homotopy can be thought of as a restriction of a much bigger story. D plus 1 basic parameters, no. Okay. D to 1 generically. And there's a point we know and love called the Bezout system. And there's the point we want to solve. Call it C hat. And we go there. Perhaps using a random given. Okay. But that picture we were drawing before embeds into this picture in a natural way. Okay. So in univariate continuation, we had just a little line segment, and that's just a little line segment in this big space.
And each point on that line segment is a solution.
Each point on that line segment is a polynomial of degree d.
Which has the same solution set, right?
And every point probably has a different solution set.
But it goes to the solution.
Upstairs, above this line segment, we have d paths. And that was the picture we were drawing before, where they start at the solutions over p hat, which are the d roots of unity. And they end at the solutions over there. Okay. So we have this like moduli space for degree d polynomial systems. Okay. All right. Ooh. Now, one cool thing about this is the way I've written, every monomial has earned itself its own coefficient here. So I really just like prescribed the monomial support of the polynomial system. So it's a copy of the integer lattice, and I've just I shaded in the elements of script A. So this corresponds to the constant term, this corresponds to the coefficient of x, all the way to the coefficient of activity. This is my monomial space. Let's call it exponent space. Good. So a multivariate polynomial homotopy continuation, MPHC for short. We do something similar. So we have some like, let's just do like two variables for now. This is some sum. Say that's the alpha. Let's see, sorry. Is we want to be in polynomials, so no negative coefficients right now. And I plus j is less than or equal to d1. Right, so these are the monomials allowed in a polynomial of degree d1. Right, so x1 to the I times x2 to the j. I plus j has to be less than d1. Let's make it a bit more concrete. Maybe we're looking at trying to solve a degree 2 polynomial and a degree 3 polynomial in two variables. Okay. So this would be like C 0, 0, comma 1. This would be C 1, 0, comma 1, where the first thing tells you the exponents, and the second thing tells you which polynomial you belong to. So for example, something like, I don't know, x squared plus y squared minus 1, x cubed minus 13x squared y plus 7. So this would correspond to just assigning numbers to all of these monomials, namely the coefficients. So I might say -1 here, 0, x squared gets a 1, xy gets a 0, y gets a 0, and here gets a 1. Right. So some of these are allowed to be 0, sure. Whereas this one would be like, okay, we got a 7 here. X squared, y, there's a -13 here. 0, 0, a 3 here. A 0, and a 0, and a 0. Okay. So we just got 3 non-zero coefficients here. Okay, but what's our super happy start system? Yeah. Well, it looks like -1, 0, and there's like a 1 somewhere, and then a bunch more zeros. Okay, this is our G1. Our G2 is like, okay, -1, a lot of zeros, 1. And it corresponds to -1, 1, and -1, 1. X1 squared times 1, x2 cubed minus 1. Okay. So by prescribing monomials, you can write down polynomial systems by just writing a vector of complex numbers. Okay, so just like here, polynomials of degree d are really encoded by g+1 tuples of complex numbers, called the coefficients. You can do the same thing with many variables and many monomials here. That makes sense?
Nice idea. Each lattice point gets a complex number, right?
Yes.
That's the idea. Okay.
And so what is, so let's assign some notation here. So we pick some support, namely A1 is going to be, you know, one, 2 will be something. Okay. And we'll write x of a dot to be the incidence variety of this parameterized polynomial system. Right, this is a polynomial system in two variables, in this case, x1, x2, and many parameters. It lives inside C squared is the solution space. D1 plus 1 choose 2 plus D2 plus 1 choose 2 in the parameter space, because that's how many monomials you have of degree d1 or less, or degree 2 and less. And it goes down to, I'll even call this. And it goes down to the parameter space. And this is d1 times d2 to 1. Because a generic bivariate polynomial system where the first one has degree d1 and the second one has degree d2 has d1 times d2 regular zeros. And this is called Brysiewicz theorem. The Brysiewicz theorem is just the parameter continuation theorem plus telling you what that n is for this particular family. So if somebody emailed you random numbers and to tell you the coefficients of a degree 7 bivariate polynomial and degree 10 bivariate polynomial, you can put it into the space which generically has 7 times 10, 70 solutions. Find your favorite one, called the Brysiewicz system, where it's really easy to solve. Take the one that they gave you in the email, draw the homotopy, and do the tracking. And that is the Brysiewicz homotopy.
Can we always do that?
Yes. Yes. And you will get all the isolated solutions. Now you may have fewer isolated solutions than the Brysiewicz count. You may not, in other words, you may not be a generic pointer. It may not be a regular parameter. In which case, you're going to have to deal with the issues you have when you're not a regular parameter. Things go off to infinity. How do you recognize that in your code? Things start crashing together. How do you recognize that in your code? Things land on positive dimensional components. How do you recognize that in the code? But as long as somebody emailed you random numbers for the coefficients, you don't even have to worry about that. You can just relax. Okay. So this is the multivariate setting. Somebody handed you a polynomial system. What family did you put it in? You put it in the family defined by the degree sequence, where you consider all possible polynomial systems with that degree sequence, which means all possible polynomial systems supported on these triangles of exponents, or with more variables, they're like n simplices of exponents. And then you found the Brysiewicz system, which is really easy. It's just like a long line segment for each simplex, right? Because it's x1 to the d1 minus 1, x2 to the d2 minus 1, x3 to the d3 minus 1, etc. Right? So it's just a bunch of line segments.
Right.
And then you tracked in a straight line, maybe with the gamma trick, to your target system.
This is off topic, but we could choose, say, simplices, some nice simple subcomplex with, could cook up some other start system which could give us answer faster.
Yeah, so that's a good question. So if somebody gave us a polynomial system with a degree sequence d1, d2, and we wanted a start system, Dr. Wall's like, maybe there's another start system we can use. Totally right. There are. But are they really going to be easier than solving x1 to the d1 minus 1 and x2 to the d2 minus 1?
Faster.
Faster than that?
I don't know.
I don't know. Yeah, maybe, yeah, but it's kind of a non-issue because it's already so fast to cook up that start system. But you're really close to something that is a real problem. And I'll tell you that in a second. Let's think about this system. I love that variety. How many solutions does this polynomial system have? x has to be 4. Now back substituting the other one, and y has to be 16. So it's 4 comma 16, only one solution. Wait, but the degree sequence is 2, 1. Right? So that means we're on the exceptional set of this
Right.
parameter space. Maybe we can find a parameter space, which is more appropriate, like a parameterized polynomial system, where we do have the correct number of solutions. So let's do A1 is just 0, 0, 1, 0, 2, 0, 0. I'm just going to choose different support. Okay, so my F here would correspond to like a 0 here, a 0 here, a 1 here, and a -1 there.
Negative one there.
And A2, maybe okay, so this is in monomial space. This is just the origin and this, so nothing else. It just lives in this x-axis, yeah. I can write the same parameterized polynomial system just with respect to these polynomials, right? I can look at the 0 set of C0, 0, 1 plus C1, 0, 1 x plus C1, sorry, 2, 0, 1 x squared plus C0, 1, 1, y. So that's my first polynomial. Maybe I'll do capital F1 of x, y, and the c's. And then my second one is much easier, right? It's C0, 0, 2, because we're in the second polynomial now, plus C1, 0, 2 times x. Okay, this is a parameterized polynomial system. How many solutions does this have? Generic. Somebody gives you generic c's. Well, I can solve for x here. It is a negative this thing over this thing. Okay, so I can solve for x. There's only one choice for x, and after I plug in x here, this is a linear equation in y. So I can solve for y. Y is just negative this part. So there's one solution. So now in my 1, 2, 3, 4, 5, 6 dimensional parameter space in the C's, this system here is a regular parameter. What's the problem? I don't have a Bezier system that I can solve very easily. Okay, so that's the problem. When you restrict your family so that your polynomial system accurately reflects the behavior, the generic behavior of the family, the thing you might run into is now I don't have an easy member of that family to solve that I can then move to other places. And you can ask all sorts of questions. For example, is there a general formula to take these supports, which are like these very discrete combinatorial things, and understand how many solutions I generically get? So that is the theorem we're going to end on today. So I'll state it. And then we'll discuss it. And we can all enjoy the cold outside. Is anybody online from University of Toronto? I don't remember. Wait, smile. Then any of you guys U of T? Okay, so it's called the BKK theorem. Nope.
No.
Okay. So one of the K's is a professor at University of Toronto. His name's Asphalt Havansky. You may have taken a Fields Academy course from him last year. The other names are Bernstein and Kushnarenko. So let A dot be a collection of monomial supports. What do I mean by that? I mean, each AI belongs to the integer lattice, but we're going to ignore negative exponents right now. It works even if you use negative exponents, so then you have like a Laurent polynomial system, which is kind of not really our vibe in this course. Okay. Good. And the number of isolated regular solutions to a generic polynomial system with support dot, and I'll put in parentheses in C star to the N is this mysterious game. So there's a function, it just depends on the sport, of course, called the mixed volume of these supports. And I'll explain what's going on here a little bit. So C star are all the complex numbers that are not zero. So this is counting the number of solutions where none of the coordinates of the solutions are zero. And that's why you're allowed to play this game over Laurent series.
I think some toric thing is going on in behind.
Yes. So example, okay, let me tell you what mixed volume is for pairs of polygons. So we have monomial support like we had before. Okay, this is our A1. Let's take our A2. That was our A2, yeah? Okay. Now we're going to go from dots to polytopes by taking the so-called convex fold. For polygons, just imagine that you have little sticks coming out of the board on each one of these dots, and you put a big rubber band around it, and you let go, and you'll get this polygon. Okay, maybe it's inappropriate for me to call it a polygon. It's definitely a polygon, okay? It's a line set. Okay. What is the volume of this? Quick, volume of a triangle. One half face same side.
One.
One. Yeah, okay. How about this one?
Oh, system.
Sorry?
It's like
What is the volume of this in two-dimensional space? 0, 0, 0. Takes up no area. Yeah? Okay. But that's not what we compute when we compute mixed volume. What we do is we add every point here to every point here to cook up a new polytope called P plus Q. So this is P, this is Q, P plus Q. I'll just start with the one that I like the best. That's this one. And then I will take this one, I will drag it around each of these vertices. Okay, and so anything, this is the polytope. Beep, boop, boop. No, it's only there. Okay. This is the polytope you get with P plus Q. You added every point here to every point here. What's the volume of this? Oh,
3/2.
3/2. And minus the volume this 1/2. Minus the volume of that 0 is,
I think that 1/2 should be 1/1.
It's reactive volume, right?
oh, yeah, okay, so then the 2 then. This is volume 1, area 1, 1 times 1. This is 1/2, 1 times 2. This is 2. This is 1. 1. This system has one solution generically, which is something we already discovered. Okay, it's smaller than the Bezier bound. And since the Bezier setting is a special case of just doing supports, right? So a triangle dilated by D1 versus a triangle dilated by D2. What is this? This is a 1/2 D1 squared, 1/2 D2 squared. And now the question is, well, what happens when you add everything there? You get a D1 plus D2 thing. It's 1/2 D1 plus D2 squared. Subtract those off. And should get D1 times D2. Because these will pop off the 2 squared terms, and all you get is the mixed term left. So BKK is a more general thing than Bézier's theorem. The study of families of polynomial systems like this, their structure, everything about them, number of real solutions, topology, whatever. People use the language of sparse polynomial systems. So sparse polynomial system solving. And that's what my thesis is about. Okay. What else can I say about this? Any questions? Let's just open it up. I think, because I'll answer whatever you're interested in. Maybe I'll let Sunday recording, then